Okay, as fascinating as all that is. Limits. So let's look at a couple examples here that are kind of piecewise function stuff. I want to look at one trig example, similar to what we saw yesterday. And then I want to show you a geometric proof of the primary special trig limit that we talked about yesterday. Okay, so that's kind of on the agenda for today. Good stuff. What about this one here? So find the limit of f of x as x approaches 2 if it exists. So what would we do? Talk to me about this. So evaluate directly? Okay, so if we evaluate directly, here's what we're going to get. So you tell me. F of 2 equals what? Say it again. Heard it, I think. It'd be 4? Yeah. And you get that from, because 2 sits on the bottom piece of that piecewise function. Yes?
But if you put 2 on the top, you get 3 times 2 is 6, plus 1 is 6, or wait, 7, sorry.
Right.
Yeah. So it's
But,
just
okay, but if we're evaluating the function, x equals 2 is part of the domain of the bottom piece, not the top piece. Because the top piece only exists when x is less than 2. Okay, so I'm not suggesting this is the answer, but it was you guys had talked about finding the value of the function at 2, about evaluating directly. Well, if we evaluate directly, we get 4.
But that's not as it approaches.
You're right. That's not a limit though, is it? That's a value at 2, and that's not what a limit does. Okay? So, what do you think? Ideas.
You have to take the top function but extend it so it includes.
What do you mean by that? The top piece?
Yeah, like somehow.
Okay, so now you're thinking about this, trying to utilize the strategies we talked about the last couple days, right? Where you're trying to maybe eliminate a hole or something. Okay, that's not going to work here though, because this is a different kind of function. It's a piecewise function. Piecewise functions are oddballs, right? They're defined as having different rules depending on where, or equations, whatever you want to call it, depending on where you are in the domain. So you can't treat this like the ones we did previously. It's not going to work, but I want you to think about the definition of a limit. Think about the limits we've talked about, and if we're trying to take a limit as x approaches 2, how are we going to deal with that in a piecewise function where 2 is the transitional number between the pieces?
Take a number that's less than 2.
Okay, so we're going to take a limit from the left.
Yeah.
Of which piece? If we take a limit of this function as x approaches 2 from the left, which piece is the ant going to be walking on as he approaches x from the left, the top or the bottom? The top, right? Because values of x less than 2 to the left of 2 are exclusively in the domain of the top piece. Okay, keep going.
So you just find the limit approaching from both ends.
Okay, because and you fill in the blanks here, for a two-sided limit to exist, what has to be true?
Well, it has to be
Okay, the limits from the left and the right have to exist and be equal, right? Okay, so then if we were to do the limit of f of x as x approaches 2, how do I write from the left? Okay, good. I have a superscript that's a minus sign, right? Good. Is equal to, the limit of 3x plus 1, that's the top piece, as x approaches 2 from the left. And what is that limit? 7.
Still.
The limit of f of x as x approaches 2 from the right is the limit of what expression?
2x times the quantity x.
And what's that equal to? 4. So, does the limit exist? No, doesn't exist, right? Because the two one-sided limits don't agree. Right? You only 5 on that, how we doing? Okay. You see the approach there though, because piecewise functions inherently have different behavior from the left and the right, evaluating a limit means evaluating from both directions. Okay? All right, something similar. How about a problem like that? So they give us some function g of x that has some parameters a and b, and we want to set those values so that this limit exists and equals 7. How could I do that? Are a and b variables?
So they'd be constant.
I mean, it seems like they are, right? Because they're things that we can vary. What we would call those, though, is not variables. We would call those parameters, because what is the variable here in this function? X is the variable. A and B represent constant values, but we just don't know what they are, right? But once we set the values of A and B, they're fixed for that function, and then X becomes our variable. Does that make sense? There's a subtle difference there. Okay? So they're really not variables, although we are going to choose their values as though they are variables. Okay? How am I going to do this one? How many unknowns? Let's try to attack this really analytically. How many unknowns do I have there?
2.
2. Okay. So what can you tell me then? If there are 2 unknowns, what am I going to need to solve for 2 unknowns?
The other unknown, or one unknown.
Well, think about this in terms of the fundamental theorem of algebra I talked about a couple years ago. If I have 2 unknowns, that means I require a system with at least how many unique equations to solve for those unknowns? 2. I need at least as many unique equations as I have unknowns to solve for the unknowns, right? Okay, so where am I going to get that system? I need to come up with two equations. What could those be?
You would isolate the 2 different equations. You'd have ax squared minus 5 equals 7, and then ax plus b equals 7.
Okay, you're right. Now your thinking is correct. I want you to be rigorous about this mathematically. How am I getting those?
Because the limit as
Okay.
x approaches 2 is equal to 7. So
Because the limits have to be equal to, both have to be equal to 7, don't they? From the left and the right. Everybody get that? So we're gonna get 2 equations as we take the limit from the left and the limit from the right. That's gonna impose conditions on A and B. So here's one. Tell me what to write here. The limit of, we'll just g of x, okay, but if we're approaching from, let's say we're approaching from 2 from the left, I'm gonna be taking the limit of what? Ax squared minus 5. Has to equal
7.
7. right? For this limit to exist, both one-sided limits have to be 7, okay? Good. So what can I do with that?
You plug in the X.
So I can evaluate that directly, can't I? Right? That's a limit that I can easily take. I get an answer. Now, my answer is going to include A's, but that's all right. A is constant, right? Okay, so agree? Right. Okay. Limit of g of x as x approaches 2 from the right is the limit of right, which is equal to, I guess I should say it this way, which equals 2a plus b, which has to equal 7. So now I've got those two equations, right, in two unknowns. So I can solve this. I can solve this linear system. Make sense? Okay, real quick, like, how would I do that?
Find A first and plug.
Sure. Find A first and plug it in. I could do that. I could solve for A in the top equation, plug it into the bottom equation to eliminate the variable A, which would give me an equation in only B. Solve for B, substitute back in, right? That makes sense? Or, I mean, then I already know A. I'm sorry, right? I'd know them both. Okay, or I could use eliminate. I could do all kinds of things, right? Make sense? Okay, all right. Good. All right, let's shift gears. Let's look at another one of these types, right? So where we're trying to, we're gonna move back to the stuff we ended with yesterday, where we're trying to resolve an indeterminate limit that involves trig functions. Remember, these are different ones. These are not ones where I'm able to cancel a factor, right? You could make that work, but it'd be very, very difficult. There's no way I'm gonna get, if we were gonna cancel a factor, it would have to be an x, right? But there's no way to get an x out of that sine 4x easily at all. It would be really difficult. Okay. So instead, we just have to rely on these two special trig limits that you're just taking as the gospel right now. I'm gonna prove that one to you. And if you can prove that one, you can algebraic, or using trig identities, you can easily derive limit 2 from limit 1. That's not that big a deal using trig identities. But we got to be able to get to limit 1 first. And so I'm going to prove that one to you today. But we don't need that yet. We'll just take it as true. What could I do here? Ideas. I'm going to rewrite this one for just a moment, though. Maybe this will help a little bit. Like, what if I take limit 1 and I write it, I'm going to write it with a theta instead of an x, which is trivial, but because I've got x's here, maybe that'll help a little bit. Okay. So the limit of sine theta over theta as theta goes to 0 is 1. And where theta is just the argument of the trig function, but it's also has to show up on the bottom. I could flip that too, by the way, right? Because isn't 1 over 1 equal to 1? Okay. Not that I need to here necessarily. What's wrong with this? Why doesn't this one match that form? It's close. But what's different about it? Yeah. What's the angle I'm feeding the trig function there? What's the argument of the sine function in this expression? What's inside the sine function? Right, that's just theta. But what's theta here?
4x.
4x, right? That's the angle I'm feeding the trig function. So that doesn't match up with the expression on the bottom, does it? Okay? So what do you think? What are my options?
You have to get 4 on the bottom. So
I either have to get 4 on the bottom, or I've just got to get an x inside the sine function. Which one seems easier to do? Would you rather do algebra inside a trig function or outside a trig function? Outside a trig function, right, for sure. So the argument of the sine is defining what our theta is. I just need to get that theta in the bottom. What are our options in algebra? We don't have very many options, really. I mean, we use the same ones over and over and over again, and one of them we use almost always, which is the identity property of multiplication. We multiply by 1, right? Because that's our multiplicative identity. So how can I multiply by 1 here in a way that's going to be helpful? 4 over 4. Absolutely, right? So I'm just going to, this would be equal to the limit of 4 sine 4x over 4x, right? Everybody agree? Okay. And how about this statement? If x approaches 0, what does 4x approach?
0.
0, right? And you could justify that by just saying the limit of 4x as x approaches 0 is 0. Okay, we don't have to defend it that way, though. We're able to just tack a 4 on there because that has to be true. If x is approaching 0, some multiple of x also is going to approach 0, right? That make sense? Okay, that looks pretty good. What's the one last thing I'd want to probably do here to make this match this guy? What's the one difference right now? It's a pretty minor one. It looks like I've almost got everything I need. There's my theta, and there's my theta. That 4. Okay, what can I do with that 4? Right, we got a property of limits here that we talked about. And you're still getting used to these, but we had a property. The limit of c times if the limit of f of x as x approaches, how do we get that not to c? Change this just a little bit. If the limit of f of x as x approaches c is L, what's the limit of k times f of x as x approaches c?
L.
L.
0.
That's our constant multiple property. What do we do with that k? It's just KL. Yeah. Right? I've got this scalar multiplying by a constant. So what's the moral of the story? The moral of the story is that's just like taking this k and pulling it out in front of the limit. Right? Remember, that's how we deal with it. If we have a constant, we just pull it out in front of the limit.
Wouldn't it just be 4 times 0 on the other one?
Say it again.
Wouldn't it just be 4 times 0 on the other one?
Well, it's 4. That 4 is going to go out there, and so we end up with it equals 4 times the limit of sine 4x over 4x as 4x goes to 0. And what is that limit equal to? That's equal to 1, isn't it? Because that's our special trig limit, right? So we just get 4 times 1, which is 4. Okay. Make sense?
Wait, how do you get 1 out of that, though?
Because it's given to us as 1. I'm just telling you, that is the value of that limit. It's indeterminate,
Because they.
right? It's 0 over 0, but it does, and we looked at a graph of it, right? So we proved to ourselves that it is equal to 1. We can see from the graph that clearly the behavior approaches 1 as x approaches 0, okay? So I can tell you're a little bit suspicious about this one, though, so let's prove it. Let's prove it. Okay. First of all, we have to invoke something called the squeeze theorem. So what the squeeze theorem says, if we have three functions, f of x, g of x, and h of x, let's let those three functions be defined for all x not equal to a in an open interval containing a, right? So they don't have to be defined at a. They might be, but they don't have to be, right? And how come they don't have to be? Because the ant doesn't care, because we're talking about a limit, right? We're going to be talking about a limit in the squeeze theorem. I guess you guys didn't know that, but we are. It's going to be a limit. So then if this is true, if for all values of x not equal to a, f of x is going to be defined as the bottom function, g of x is the middle function, and h of x is the top function. In other words, g of x is going to be greater than or equal to f of x and less than or equal to h of x on that interval. So they don't cross over each other at any place. They'd have to look like that. Okay? If that's true, then f of x, if we know that the limit of f of x as x approaches a is L, and the limit of h of x as x approaches a is L, if both of those limits converge to the same value, then doesn't it make sense that the limit of g of x is going to have to be squeezed to that same value if it's bracketed by those two functions? Everybody get that? Okay. That's our squeeze theorem. Really valuable theorem. It seems like it's just pretty much common sense, but very valuable. Okay, we're going to use that. So let's look at, I want to just kind of, this is going to seem pretty arbitrary, but on the unit circle, it's a little bit too big. Well, okay, there's my unit circle. I'm going to define some angle theta, and we're going to look at the rectangle formed by the angle theta. The hypotenuse is going to be the radius of the circle, which is 1, and the x-axis. Okay? So agreed that for this triangle, this isosceles triangle, the lengths of both of those legs are 1 because they are radii of the circle, right? Okay? So then I want to know the area of that triangle. What's the area of a triangle? Yeah, 1/2 base times the height. Okay, so the area then of this triangle should equal 1/2 times the base times the height, h. Okay, well we got to figure out what that height h is. So this is the height h right here, this distance. How could I define that? What I'd like to do is define that in terms of theta. Because what I'm ultimately going to do here is I'm gonna want to let that theta approach 0. So we need to have a theta. You'll see why here in a little bit. But we want to anchor those areas to the variable theta. Okay. How could I do that? Okay, what comes to mind if you're thinking about a triangle, the sides of a triangle, the lengths of the sides of a triangle, and an angle?
Cosine.
Usually you're thinking about SOHCAHTOA stuff, aren't you? Right. Okay, but what kind of triangle do we need if we're talking about SOHCAHTOA stuff?
A right triangle.
A right triangle. Okay, well our original triangle is not a right triangle. But could we find a useful right triangle that shares the same height with our triangle?
Yeah,
What would that be?
dotted line mark.
Okay, so that makes a right triangle, doesn't it, right? So look at this, so we've got this right triangle then. Now, the hypotenuse of this right triangle is 1. The base is no longer 1 though, right? We don't know what that is, okay? But we don't necessarily need the base, right? Because if we pick the appropriate trig function, I can find the trig function that relates the opposite leg and the hypotenuse. What trig function is that? So the sine, cosine, or tangent of an angle involves the ratio of opposite side length and hypotenuse. What was it? Sine. Yeah, okay. So sine theta equals opposite side length over hypotenuse, right? Okay, so the sine of theta would then equal, we're calling h divided by 1. Aha. So sine theta equals h over 1, so it just equals h. Aha. So that is the height of this thing, right? So the area of this blue triangle then is just 1/2 times 1 times sine theta, which is the same as sine theta over 2. Agreed? Pretty good with that? Okay. And I think, do I have that stuff up here? Yeah, there it is right there. Okay. All right, here, I'll tell you what I want to do. I want to be a little sneakier about this next page. Let's see.
Can I use the marker?
Yeah. Okay. There we go. Much better. Okay. Okay, what about this one? Now, what if we pick the sector formed by the angle theta? I want the area of the sector. Okay?
Can you remind us what a sector is?
So a sector is that. Sector is a piece of pizza. Sector is, it's a portion of a circle defined by an arc length. Okay? That's a sector. Using technical terms, it's a piece of pizza. I don't want to get too technical. So what's the area of that sector? You probably don't remember the formula for the area of the sector, right? Okay, but formulas are just, I mean, it's just wasting brain cells to memorize formulas. Just derive it. You come up with this. It's the area of that sector. And then we'll kind of use that to maybe come up with the formula for the area of a sector.
Yeah, you have to know the radians.
Okay, right, so theta has to be in radians, good. And let's do something else here. Let's say, let's take a circle that's not necessarily a unit circle, for example. I can do this. Let me,
Into the V's and then do it and then change it back to radians.
so let me take, there we go. Okay. Did I have something hidden back there? No, oh gosh, they messed it all up, didn't they? There we go, okay? So let's go down here, and in this triangle, we're not going to say the radius is 1, we'll just call it r.
Oh, x equals to r.
how am I gonna come up with the area of that sector? Theta, I mean, close. I'd be creative here, come up with a way of,
Like,
there's a couple ways you could do it. There's one way that I think would be the easiest.
do like a half circle and then take it.
Okay, well now, if it were a half circle,
Can we do just like, pretend it's a triangle, but the height is an arc length instead?
you can't do, you mean pretend that chord was an arc length? They're a little different though, aren't they? There's another way to do this. I'll give you a hint. What's the area of that entire circle? What's the area of the circle? Okay, so there's a pretty good hint.
Okay.
But then like, you have to find like that much of the circle?
Yeah.
So you
What
divide
fraction
by-
of the entire circle is that?
1/8.
Well, I mean, you don't know, you can't tell me exactly, because you don't know the value of theta. But it's, what fraction of the entire circle is represented by that sector? How do you get, 1 over theta? How are you getting, but that's pretty specific. You're telling me an exact value, and I would claim you can't do that, because you don't know the value of theta. Oh, and you said 1 over theta? No? You had a theta in there, which is good. Okay, what's useful here is to think of a specific example and then just ask, like follow your brain's logic. So what if you did know the value of theta? What if that were pi fourths? What fraction of the entire circle would that be?
1/8.
How'd you get that?
Because the whole thing of the circle is 2 pi.
Okay, so pi fourths divided by 2 pi would have been 1/8, right? Okay, pretty good thinking. But you don't know what the value of theta is. That's it, theta over 2 pi, right? Right? Everybody get that? Okay, so the area of the sector then is just theta over 2 pi times pi r squared. Well, look at that, the pi's cancel, and so we just get theta r squared over 2, which is the formula for the area of a sector. Right? Okay? So you don't really need to memorize it. I mean, you can always just derive that. Okay, but what's unique about this one? This is helpful here. What's the radius?
1.
Okay, so then the area of this sector is just going to be pi times 1 squared. Oh, sorry, theta, not pi. Oh no, it's going to crash. I know it's going to crash. What's that going to be if r is equal to 1?
Theta over 2.
Theta over 2. Okay, good. We're getting there, right? Okay, now what could you tell me about the area of this green sector so far compared to the area of that blue triangle? Both defined by the same angle theta.
One has a sine and the other one doesn't.
Okay, but what about the areas, a comparison of the areas? Okay, so the green sector is going to have a larger area than the blue triangle, correct? Okay, good. Oh, good, that one's already, okay. Okay, what about that triangle that's also defined by that same angle theta? First of all, how does its area compare to the others two?
Bigger.
Bigger, okay. So really all we need to do then is somehow come up with an area expressed in terms of that angle theta. Okay, well, Triangle, what's the area of a triangle? Okay, 1/2 base times height, good, I like it. So, base is 1, right? Height is different h, but we're gonna call it h. Do there. Yeah, use tangent, wouldn't we? Right, because we know tangent of an angle is equal to the ratio of opposite leg over adjacent leg. And the adjacent leg has a length of 1. Yeah, okay. Right, so then we could say tangent theta equals h over 1, which is just h. Aha. Okay, so now we have area equals 1/2 h times tangent theta, which is the same thing as tangent theta over 2. Okay, good. So now we've got some ordered areas, smallest to biggest, blue, green, red. Okay, and we know what those are. Can't remember how much I got it. I don't want to give too much away. I want you guys to come up with this. I don't want to give it to you. Okay, good. I don't have anything else, so we'll have to take it from here. Okay, so then we know that from smallest to biggest, it looks like this. The blue area was just sine theta over 2, right?
It's frozen.
Oh, it's broken. Yeah, I wonder. Thank you. So sine theta over 2 is going to be less than or equal to the area of the sector, which was theta over 2, right? And our biggest area was tangent theta over 2. Okay, good. All right, now what are we trying to do here, though? Think what we're trying to do. We're trying to coax out of this that limit. Ratio of, in our case, sine theta and theta, right? Right, see what I'm saying? So we got to go back here. Now we have to think algebraically, how are we going to accomplish that? Okay, so now what?
Would you get rid of it being over 2?
Yeah, can't you?
Well, yeah, we want to do that for sure. So we could do that by just multiplying everything through by 2, right? And if I have inequalities multiplied by a positive number retain their direction, right? Okay. And if we take theta to be, there's no reason that we couldn't just take theta to be a positive number, and we're just going to approach 0 as theta remains positive. Okay. So we definitely want to multiply everything by 2. What else could we do here? Because we're trying to get, we want to scrutinize the relationship, the limit of sine theta over theta, right? Or its reciprocal.
So wouldn't you try to take theta out of the problem?
We can't take theta out of the problem. Say it again.
What do you take sine and tangent?
Yeah, okay, but sine and tangent, those could be messed with, right? What if we were to multiply the entire thing through by 2 over sine theta? Look what that's going to do. That's going to accomplish some good stuff. That's going to cancel all the 2's. And when I distribute that sine theta through, what's that going to become? 1, right? This one's going to be theta over sine theta. Well, and the other one now, tangent is sine over cosine, right?
So
just cosine.
So it's just 1 over cosine. Yeah, okay. Okay, that's looking pretty good, but it's a little awkward having those trig functions on the bottom, especially that cosine. So why don't we take the reciprocal of everything? Now, what's that going to do to the directions of the inequalities, though? It's going to have to flip them, isn't it? Right. And just as a quick example, this is a true statement. 2/3 is less than 3/4, but if I flip those, what happens?
It's just big.
Yeah. Okay, makes sense why that has to happen then? Okay, so we'll flip all these over, and then we get 1, flip that sign, sine theta over theta, we'll flip that sign, cosine theta. Okay. Last step in my proof. What do we do?
Well, wouldn't you know that the middle equals 1? Since it's just sine x over x, it's sine theta over theta.
Okay, but-
You just
But
say-
we're trying to get to that.
Oh,
Right, we're trying to get that, exactly. So how are we going to get that?
Oh, so you would multiply by theta.
Well, all we need to do is apply that squeeze theorem. How am I going to do that? Okay, the limit of cosine as theta approaches 0 is what? What's the limit of cosine theta as theta approaches 0? You just evaluate it directly. What's cosine of 0? 1, right? Okay, so then this is true, right? We know that the limit of cosine theta as theta approaches 0 equals the limit of 1 as theta approaches 0 equals 1. Right? So by the squeeze theorem, what does the limit of sine theta over theta have to equal? 1. Oh, we got it. Every day I get to drop a pen in here so far.
Is calculus a bunch of proofs the whole time?
Well, it's a lot of proofs. I'm not going to drag you through a ton of proofs, but I want to do something.
Are the triangles on the sector just like what the functions look like in that?
Give me 1 second. Let me just turn off this recording.